Today we will discuss about this nuclear fission process. Start from here. Nuclear fission. So this is you already know what is nuclear fission. So if you have any X nuclei that will be going through this fission reaction, then it will become two almost equal nuclei. Let's say Y and Z. Okay. So this is the parent nuclei. We call this as the parent nuclei. And these are the daughter nuclei. Daughter nuclei. And this daughter nuclei will be having similar size. Okay, these two will be having similar similar in size. So they are similar in size. This Y and Z. Okay, so which means that their mass number will be almost same. If they are exactly same, then it is called a symmetric fission. Okay, if it is not exactly same, then it is called a symmetric fission. So let's say that A, if you say A is going to become something like A by 2 plus A by 2. So this is this kind of fission we call a symmetric fission. Symmetric fission reactions. So which means that their mass number will be just half of that parent mass number. So if those nuclei which are formed, which are the daughter nuclei, if they are having same size, okay, and the size is obviously depends on those mass numbers, number of nucleons. So if they are having same size, these daughters are having same size, then such fission reactions are called as symmetric fission. And sometimes it may be having some difference, that mass number will be some difference. So in those cases, the fission reactions are called as asymmetric fission, so that the product or the daughter nuclei will be having different sizes, so different masses. Mostly we can have that asymmetric fission, because the product, the daughter nuclei will not be having same size. One will be larger and the other one will be smaller. But sometimes we can also observe these symmetric fission reactions, where you can have that similar mass nuclei as your daughter, I mean in the product part. Okay. So now we'll discuss what is actually happening for this particular nuclear reaction. So if you consider that binding energy per nucleon curve, just insert this. So if you consider this, okay. If you consider this binding energy per nucleon curve, binding energy per nucleon, then that will be almost looking like it will almost start from 0 and it will go like this. This is an average behavior I am just drawing here, and then it will again go. And maximum, then it comes back almost like this. It will not be having this much slope anyway, so almost it will be almost like this. I will draw it again, so it has to be somewhat. Should go a little more here deeper. And then go something. So almost like this. Okay. So this side you have that binding energy per nucleon, and here in the x-axis you have that mass number. So binding energy per nucleon versus mass number curve. Okay. This is this one you have. We discussed about this when we discussed that liquid flow model itself. So you are well familiar with this. So this maximum will be around 8.9. So this is 8.9 mega electron volt per that mass number. Okay. And this is 8.9. Then an average value will be so around this. I'm saying around this an average value if you take. So that will be around 7 point, sorry, 8.6 or 8.5 range. So this will be around 8.5. Let's say this average value. So this scale is not up to that, but just this is a rough sketch of that. And if you consider any lower value, that will be around 7.5, 7.6, that range. I mean this around this region. So this lower one, these nuclei which are here in this region. So they will be having this 7.5, 7.5, 7.6 mega electron volt per mass. So this is the binding energy per nucleon versus mass curve. So you have that maximum value which is equal to 8.9, and average of this nuclei, that is most of the nuclei will come around 8.5 this range. Okay, and the this extreme nuclei, they are having very large mass number. In this you can see mass number is very large. At the end of that periodic table or mass number, when you consider the most heavy nuclei, those nuclei will be having around 7.6 of mega electron volt mass number. Now in this side we have that heavy nuclei like uranium. Normally we can have that this uranium 235 natural uranium, or you can have that uranium 238, all those things. So you are here, you will be having 92 atomic mass number, atomic number, all that. So anyway, this nuclei, they are having very large mass number, very large in size. Okay, in this side. So they will be having binding energy per nucleon of around 7.6. Now what will happen if you consider this nuclei? This nuclei in this end. So they try to split into two different nuclei. smaller nuclei, and they try to come to here, this range. So this process is called as fission reaction, because this large nuclei, they will split into some smaller massive nuclei, and they will come to this region. So what will happen when they will come from here to this region? When they comes to this region, their binding energy per nucleon will increase when it is in this region. So for that, they will split heavy nuclei. They will split and become smaller nuclei with a small mass number. Let's say in this range, you can see that, especially in this point. Okay. So they will become their original mass number will shift into some small mass number, and they will become more stable, because in this range, in this region, we have more binding energy per nucleon, so they will be highly stable. And in this range, you have less binding energy per nucleon, so they will try to split the nucleus and will become smaller nuclei, and try to come to that most stable part, or they will try to increase that binding energy per nucleon. So that is what is happening for fission reaction. So let's say this is a heavy nuclei. So this heavy nuclei split into smaller nuclei. So this will be having some hundred and some few hundreds of, I mean some 130 or 120 of mass number, these nuclei. Okay, so they will come in this range of mass number. I mean binding energy per nucleon for this much of binding energy per nucleon. So there will be an increase in binding energy per nucleon while splitting that heavy nuclei and becoming to some smaller, lighter nuclei. Okay, so that's why this nuclear fission happens. That nuclei will be very large. Number of nucleons are large. Number of protons become large. The Coulomb interaction will be very strong, and that will leads to that Coulombic repulsive force inside the nucleus, because of more number of protons are there, more number of positive charges are there. So when they exceed that average nuclear force, they will become unstable, and it will make them break into two different nuclei, and that convert their binding energy per nucleon to some higher level, so that the nuclei, this doctor nuclei will be much more stable. Okay, so that is the basic nuclear fission process. And now let's consider the Q value of this particular reaction. Q value means the energy released in this particular nuclear fission reactions. Okay, so initially it was observed that this is a naturally occurring or spontaneous fission reaction, when one nucleus uh, spontaneously becomes two different nuclei. Okay, this can be made artificially also by hitting some high energy particle to some heavy nuclei, and that nuclei will convert into some smaller nuclei. That is also there. So initially they have done some experiment like neutron, which are bombarded with this uranium, which are hitting these neutrons. Uraniums are there, and neutrons are hit from a neutron source with some high energy neutrons, and that will cause formation of barium Okay, so this barium has some 138 mass number, and you can have this uranium as you 235 or 238. So that will form this barium. Initially, they thought that this barium, this is kind of another nuclei, another nucleus with some similar behavior of barium. In the first observations, initial observation of these nuclear fission processes, they thought that this is the nuclei which is formed after that uranium which is bombarded with high energy neutrons. Okay, and that formed some different kind of nuclei which are having some properties of barium, but then later they confirmed that this is not just like barium, it is barium itself. Okay, so it is actually that uranium which is converting into barium. That is what is happening in these reactions. So these are the initial nuclear fission processes that were carried out by these nuclear scientists. And when you consider that Q value for this reaction, which means that how much energy uh, is released in this nuclear fission process, for that we have to consider those mass energy of nuclei and binding energy of nuclei. Then you take the difference, and we can calculate from that how much it will be. So for that, let's consider let's consider some let's say nucleus which is X, paranuclei X, which is having some mass number A, which is going to through this nuclear fission reaction. Okay, through this nuclear fission, and that will become some Y and Z nuclei, daughter nuclei, with mass number, let's say A1 and A2. Okay, in such a way that A will be equal to A1 plus A2, so there is no decrease in mass number when you consider the daughter nuclei. Sum of that mass numbers of daughter nuclei will be equal to that of paranuclei. So A will become A1 plus A2. Okay. Now, if you consider that energy of this nuclei, what will be that? Energy of nuclei will be given by energy of the nuclei, nucleus, I should say. That will be nothing but let's say if the nucleus is having mass m, and mc square will be that energy, that will be equal to, so m here is that nuclear mass, that will be nothing but zmp. So this z is the atomic number times mass of proton plus number of neutrons times mass of neutron. So this is the total mass of that nucleons inside that nucleus, and this has to be multiplied with c square, that is the total energy of that uh, nucleus. I mean, if you consider one nucleus, so the energy will be nothing but the energy of the nucleons inside that nucleus. So there will be number of nucleons, and this number of nucleons will be total number of protons and neutrons. Okay, so if you want to calculate what is the mass associated with the total number of nucleons inside the nucleus, that will be the total number of proton times mass of proton plus total number of neutron times mass of neutron. So that is what we have written here. Okay, so this is the mass, this is the atomic number, that is the number of protons which is multiplied with the mass of a single proton. So we'll get the total mass of protons, and here we have a total number of neutrons times mass of a single neutron, that is nothing but the total mass of neutron multiplied with that c square, that will give you the total energy associated with that nucleons. But this is not the total energy of nucleus, because some amount of energy from this is used for binding energy, used as binding energy to hold those nucleons together. and that binding energy has to be decreased or subtracted from this total energy. That will be your nuclear energy of that nucleus. Okay. Now, if you consider the same scenario for the daughter nuclei and parent nuclei, so for parent nuclei, for parent nuclei, I should say parent nucleus. So for parent nucleus, it will be this M will become mx. Okay, so this M will become mx. So this is mx times c square because x is the parent now. Similarly, one more thing is that when you, if you want to find out what is the Q value of this particular reaction, okay, then you had to take difference between all these energies that will give you that Q value. Okay, let's in terms of that mass energy, if you consider, I should write, you calculate that Q value. That Q value will be nothing but mx mass of that parent nuclei minus mass of daughter nuclei minus mass of second daughter nuclei. So it is just the difference in masses of that parent and daughter nuclei. Then this times c square. So this will give you that Q energy, Q value. Okay, that fission reaction. Okay, so let's consider this mass of nuclei for the case of sorry, energy of that parent nuclei, that will be mx square. Mx is the mass of that parent nuclei, and this will be equal to first we have zmp, okay, plus nmn, that these are the mass and sorry, neutrons and protons associated with that parent nuclei. This times c square minus, and this binding energy for parent nuclei, that will come that X parent nuclei is the heavy nuclei that we are considering, those uranium type nuclei, which are very large in size, and their mass number will be larger. So we are considering this nuclei, the nuclei which are here. These are the uh, parent nuclei, the heavy nuclei. So their binding energy per nucleon will come around 7.6 mega electron volt per, so that per nucleon. Okay, so that we have to consider here. So from here, what we can say, that binding energy of that parent will be, binding energy will be 7.6. So this is binding energy per nucleon, 7.6. So if you multiply this with that mass number, then you will get this binding energy. Okay, so their binding energy will be 7.6 times A, because binding energy per nucleon, that is binding energy by that mass number, will be equal to 7.6. So binding energy will be nothing but 7.6 times A. So that we have to substitute in those equation. Similarly, if you consider that daughter nuclei, so it will be around 8.5 mega electron volt, because these nuclei which are heavy are converting, or after that nuclear fission, it will become lighter nuclei which are having this average energy of 8.5. Okay, so for daughter nuclei, the binding energy will be I should say bx. This is for daughter nuclei. This will be coming around 8.5 times A. So this is the binding energy for those daughter nuclei, if you consider that they are having similar kind of mass number. So that we have to consider. So this binding energy for parent, it will come around minus 7.6. Okay, 7.6 times A. So this will be 7.6 times A. This much of mega electron volt. Okay. And if you consider this for daughter nuclei, for daughter nuclei, there are two of them. So let's say first case we consider myc square will be let's say z1 for the first one. So z1 mp plus n1 mn times c square minus, here it is 8.5 mega electron volt times a. Similarly, for the second one, mz c square, mz c square will be nothing but z1 we consider, so here we consider z2 times mp plus n2 times mn, this much multiply with c square minus same uh, binding energy will come, because those nuclei will be coming in that average energy region, average binding energy per nucleon. Okay. Now, if you take the energy difference between these values, okay, then you will get that Q value. So Q value will be nothing but you take those energy difference between this parent nuclei. Okay, that is, I have already written that mx c square minus my c square minus mz c square, or I will write more for more clarity. I will write like this. Okay, so this is the parent nuclei energy mx c square that has to be decreased, subtracted from that daughter nuclei energy. Then what is the remaining energy that will be coming out of that reaction, that is used by those daughter nuclei. Okay, so when that x undergoes those this nuclear fission process, okay, so this will become one y nuclei and one z nuclei. So this y will be moving in one direction, z will be moving in the opposite direction. Okay, so just opposite direction. So it will be, so it should be like just opposite to that. If that x is at rest, let's say x is at rest, and that fission process is happening, fission reaction is happening, and if y is going this side, this direction, okay, then this z will be going just to that opposite direction. So with the kinetic energy, from where it will get that kinetic energy, that kinetic energy will be given by this q value, q energy. So when this x is going to become one y and another doctor z, and if you calculate the energy which is associated with this is mxc square, this is myc square, this is mzc square, are the energy associated with this nuclei. And if you calculate what is this mxc square minus myc square plus mzc square, that is the product sum of those product nuclei energy, and you can find out that some energy is less. Okay, some energy is less than those mxc square. If you add these two, myc square and mzc square, if you add those energies, then you can easily find that it is less than that of mxc square, and that energy which is reduced will be used as the kinetic energy of this daughter nuclei to move in the opposite direction. So that energy is nothing but your Q value of that reaction, that will be given by the parent energy, which is subtracted from the daughter nuclei energy, that is myc square plus mzc square. So this is mzc square. Okay. So this again can be written as so mxc square we have here. Okay, we have that mxc square here. See, okay, this one. myc square is here, mzc square is here. So you substitute those values in this equation for calculating q value. Then you can have if you take these terms, then this term will become 0. Okay, anyway, I will write here, so you don't have to confuse that. Mn c square, and this has to be decreased from that z1 mp plus n1 mn times c square. Again, it has to be minus decreased from that z2 mp plus n2 mn this times c square. Again, you have that binding energy term. So only we considered these terms now. These three terms we considered. Now we have this binding energy term. So we have minus 7.6 times A. So here we have to take minus 7.6A, minus 7.6A. Then again one minus will come because mx c square minus these terms you have to take mx c square minus my c square plus mz c square. So this mx c square has one minus 7.6 that we have written. Then you take minus of my c square plus mz c square, that will come this will cancel this minus. So minus of minus 8.5 will come, minus of similar to that second term. So that will result in plus 8.5 a plus 8.5 a. So two times. Now, if you calculate this, what is this q value will come? And that will come, you consider this z. Z is nothing but z1 plus z. Remember that z1, z is nothing but z1 plus z2. That is the doctor nuclei atomic numbers you add. That will give you that parent nuclei atomic number. That is number of protons. And if you consider n also, n will be equal to n1 plus n2. Okay, so these terms will become 0 because z equal to z1 plus z2 here, and n equal to n1 plus n2. So if you take these three terms, z1 plus z2, I think I minus my c square plus, okay, here we have z1, yes, minus z1 minus z2, so that will become minus z1 plus z2. Okay, so z1 plus z2 will be z, so z minus z1 plus z2 will come here, so that will become 0. Similarly, n here, we have n here, so minus n1 plus, so it will come like this, so just z minus z1 plus z2 times mp or this factor will be coming, and n minus n1 plus n2, but this is nothing but z and this is nothing but n, so that will become 0. Okay, so these three terms will become 0 and remaining will be minus 7.6 plus 8.5 times a. So that we have to consider a okay, this one we have a1 here, this one we have a2 here, so okay, now it is okay. So these are the expressions that we'll get. Now remember that a1 and a2 also, so a will become a1 plus a2. So a is nothing but a equal to a1 plus a2. That is the mass numbers of daughter nuclei. You take that total mass number of those daughter nuclei a1 plus a2. That will be equal to mass number of the parent nuclei. So if you consider that a1 plus a2 will become a, then your total expression will become minus 7.6 a, then plus 8.5 times a, because that 8.5 a1 plus 8.5 a2, this expression. So this expression will come this one, 8.5 a1 plus 8.5 a2 will become 8.5 a1 plus a2, and that will a1 plus a2 will become a, so that 8.5 a will come. And if you calculate this, minus 7.6 plus 8.5 a, that will give you something like 0.9 a, right? So that is the Q value that we'll get 0.9 times A. I think we have okay. So this is mega electron volt. This much of mega electron volt will come when you multiply that with mega electron volt per A. You have to consider so 0.9 times A will become mega electron volt. So this much of mega electron volt you have to consider for the case of this much of mega electron volt of energy for Q value, for your Q value. Okay. For this part, so when you have different mass number A value for your parent nuclei, then your Q value will also be different. Let's say, for example, your A is equal to some 240 in the range of that uranium nuclei, then your energy will be that Q value will become almost 240 times 0.9, 240 into 0.9. So this will give you almost some 216 mega electron volt. So this is the Q value of this particular reaction when your A equal to 240, and this much of energy will be released in that nuclear fission process around for the case of A equal to 240. If you use uranium 240 nuclei, some heavy nuclei, then that will give you this much of energy released while those nuclear fission process, 216 mega electron volt. So in this particular case, if you consider that Q value, this is positive values, 0.9A, which are positive. Okay, these reactions are energetically favorable. These reactions are energetically favorable. These reactions are energetically favorable. So that means if you consider that A values, these A values, okay, and you calculate that Q value which is coming as positive, if it is coming positive, then those nuclear fission processes are favorable, which means that the fission process will happen spontaneously. Okay, so we do not need any this kind of reactions does not need any supply of energy. These reactions will happen spontaneously. Okay, so now we will calculate when this Q will become that favorable to that spontaneous reactions, for which mass numbers they will be in favor of that those reactions, and for which mass number they will not be having that much favorable conditions, which means that we have to give some energy, then only some cases that fission reaction will happen. Okay, so this Q value that has to be positive, then only we will get that nuclear fission, spontaneous nuclear fission. So in other cases, we have to supply energy to those nuclei, and then the reaction can be possible. So here we just considered that binding energy of nuclei as 7.6 initially. Okay, remember that. So we consider that we are taking heavy nuclei like uranium in this regime. Okay, and we took this nuclei with some binding energy per nucleon of 7.6, and then we did all those calculations, and we considered that for this particular reactions the Q value will be positive. Suppose if you are considering any other nuclear reaction, for example, if you consider any point here, okay, and we are assuming that is going to convert into this portion, and that is not going to happen because the binding energy per nucleon those for those nuclei in this region will be higher. So it depends on that binding energy of the nucleus that we consider initially, that is our parent nuclei. That is important. And then only we consider the 7.6, 8.5, all those values, energy, binding energy values. So it depends on what values we consider here, that q value, whether that q value will be positive or negative. So if that q value is positive, then they are energetically favorable. Those fissions are energetically favorable, and the fission process can happen naturally. Okay. In some cases, this binding energy of parent nuclei will be higher, and this binding energy of daughter nuclei will be smaller, or any such kind of actions happens. Then such fission process will give you Q value which is negative, which means that we have to supply some energy in order to have such kind of nuclear fission process in some kind of in some nuclei. So that we will consider now. In what cases this Q value will be positive, and in what case it will become negative. So for that, we will consider some symmetrical uh, fission process, symmetric fission process. So let's say that for symmetric fission, we'll consider now for symmetric case. So for symmetric case, which means that the A1 value will be equal to A2 value, that will be equal to A by 2, which means that the mass number will be just half of that parent nuclei mass number, nucleus mass number, for this product nuclei I'm saying. So A1 is nothing but that first daughter nuclei, A2 is the second mass number correspond to that second daughter nuclei. So that will be equal to just half of parent nuclei mass number. So this then the fission is nothing but the symmetric fission. So it is just half of that parent nuclei. Okay. So if you consider this scenario, and then we can take let's say M. In this particular case, if you consider the energy, okay, then we can take mass of mc square, that is the energy of that parent nuclei, that will be nothing but z times mp plus n times mn, this much of c square minus binding energy. This we already written before. So considering that binding energy term, so that binding energy will be nothing but, you consider that semi-empirical mass formula. So that binding energy is coming as AV times A from that semi-empirical mass formula I'm saying. So binding energy is nothing but AV times A minus AS times A raised to 2 by 3. This is that surface term. Okay. Then we have that Coulomb term. Remember, AC times Z into Z minus 1 divided by A to the power 1 by 3. Okay. Then we have again minus A asymmetric term. So can you say A? So this will be n minus Z whole square divided by A, and plus that pairing term, plus pairing energy also will be there. So this is coming from that semi-empirical mass formula that we already know. Okay. Now consider different terms here. First term, that is volume term. Second term is that surface term. Okay. Then we have Coulomb term. Then we have this asymmetry term, that the number of neutrons and number of protons will not be same when you go for a higher nuclei. So there will be some asymmetry in the number of nucleons. Okay, that is contributing to this term. Okay. Then that pairing energy, even nuclei, then it is positive, odd even. So that we have to consider. That is for pairing energy. Okay. this part. So in this present treatment, we will not consider this section because let's say we are considering even nuclei. Okay, even nuclei, which means that the mass number which is equal to even. Okay, so even nuclei. So number of protons and number of neutrons equal to even, that we are considering here. So pairing energy we are not considering, and in this particular case, because we have taken A1 equal to A2 equal to A by 2 here. Okay, so the mass number here is even. We are considering even mass numbers. Okay, so then we have, then only we can take that A by 2. Otherwise, if it is A equal to odd, then let's say 135, then you do not have that symmetric kind of fission under this condition. Okay, so let's say A equal to 130, sorry, we can take some heavy nuclei. Okay, so let's say 235, that is an odd number, which is an odd even nuclei. So if it is an odd even nuclei, then that A will not come as even, capital A. Then if you take that division by 2, then assigning that value for A1 and A2, that is not possible because it will come as fraction. So let's consider even nuclei, or let's consider for the case of A, which is even. So in this particular case, we are not bothered about this pairing and this particular calculation. Okay, and you consider this AV times A. So this is nothing but that volume energy we discussed about this during that semi-empirical mass formula. So if you consider heavy nuclei, okay, and that is going to become smaller nuclei in that fission reaction. So number of nucleons inside this nucleus and the number of nucleons inside these two nuclei, if you take that sum, then they will be same because we are taking symmetric fission reaction, and A1 equal to A2 equal to A by 2. So if you consider that, then A will be equal to A1 plus A2 in this particular case. So that will give this total volume of that nucleus will remain same. When they split, the total volume will remain same. So the volume energy, okay, for the parent and nuclei, if you take that total for nuclei, total volume energy of corresponding to that both daughter nuclei, if you consider, that will be same. Volume energy for parent nuclei will be equal to volume energies of sum of volume energies of those daughter nuclei. So volume energy will not change in the fission reaction. Okay. Now consider that surface term. If you consider that surface term, there will be an increasing in that surface energy. Okay, because when you have that fission reaction, you are getting two sphere. If you consider that nuclei are spherical structure like a liquid rock model when you considered. So then in that case, you will get two different spheres with different radius. If they are symmetric fission, they will be same radius, but we have more surface area this time because we have two different spheres. So obviously that surface area will be higher than that of parent nuclei. So this will be different for parent and daughter nuclei. So when it is heavy, there are lot number of protons are larger, and Coulombic repulsive force will be larger, and Coulombic potential will be larger. So that energy from that Coulombic potential will be larger in when it is having high huge size, or the mass number is larger. But when it fission happens, when happens and it will become the daughter nuclei, the size will become reduced. A number of protons in each of these daughter nuclei will be lesser, and the Coulombic interaction will be smaller. Okay, so there will be a difference when you consider that parent and daughter nuclei. Coulombic interaction will be different. So we have a difference in this term for those parent and daughter nuclei. Okay, so these two terms. Okay, I will draw it in different color. So this term and this term we have difference. when you consider that parent and daughter nuclei. Considering the next term, that is the asymmetry term, when you consider the number of protons and number of neutrons which are deviating. So for that you can substitute, let's say this part, this thing. So this will be nothing but A times for doctor nuclei. How it will come? Let's say this is for parent nuclei, n and z for parent nuclei, n minus z square. So let's consider for daughter nuclei, it will be n by 2 minus z by 2 divided by a by 2. So this much of square. Okay, for one daughter nuclei. So there are two types, two of them. So it will be 2 times a n by 2 minus z by 2 by a by 2 for daughter nuclei, I'm saying. So that daughter nuclei collectively we will be having this much of contribution towards that asymmetry energy. So now if you consider this, this if you take, oh, this square only apply for here. Sorry for that. So a by 2 is different. So a by 2 is in the denominator, which is not having that square part. Okay. So we are considering that daughter nuclei now. Okay. So don't confuse here. Considering that daughter nuclei. So for that daughter nuclei, n will become n by 2, and z is nothing but z by 2, and your a is a by 2. Okay. Just replace this term, asymmetric term, like this. And there are two such nuclei, two daughter nuclei. So I have to multiply that term with 2. Okay. So now you take that square. This will become, this 2 will come here. This 2 will come here, that in the numerator. So that will come 4 times a into that n by 2 minus z by 2. So if you take that squares, there will be 4 which is coming. Okay, some 4 will be coming in there. So that you can take as common. That 4 will come. So that 4 and this 4 will get cancelled each other. This 4 I'm saying. Or you can directly take this 2 square outside. So that 4 will come here. Then you have that sorry, n minus z square and divided by a. So this 4 and this 4 get cancelled, and you will get the same expression as here. So for that term, asymmetric term, there will not be any change when it convert into that daughter nuclei when the fission happens. So asymmetry term also there is no change, and we are not considering that pairing term here. So only these two terms are different for both the parent and daughter nuclei before fission, which means that before fission and after fission, the symmetry term and Coulombic term are different. Okay, so now consider that energy of that nucleus. Okay, this one I'm saying. So if you consider that energy of the nucleus, only this term will be having some difference. All other terms will remain as it is. So mc square will become some rest mass energy. I will say that this part. Okay, this part. I will took it as m0 c square for that energy, and some plus c will be coming because of the this term AVA and this term, and you can also take pairing energy, but you do not have to consider that. So these two are constant now for both the parent and nuclei. So I will take that summation as C, that is for volume energy minus that symmetry energy. I just took as C. It's a constant for both, which is same as for both parent and daughter nuclei. So I will just take it as C. Then we have minus binding energy we had to consider. Okay, so then we have that terms minus of minus as a raised to 2 by 3, then minus ac z into z minus 1. So that z into z minus 1, I will just take z square, because z into z minus 1 When you consider, this will become z square minus z, z square minus z, right? So for heavy nuclei, I can just simply write this z square minus z is almost equal to z square. Let's consider, for example, your z value is somewhere, let's say 100. Okay, in that case, it will come as 100 square minus 100. So this I will assume this as almost 100 square. There will not be much difference in that. For that z minus 1, okay, z into z minus 1, or you can simply take 100, let's say 100 minus 1. Okay, this is just like 100 and 100 into 100 minus 1, that's z into z minus 1. So this is somewhere, this is 99. Okay, and this will become 100. Okay, this way also you can treat all the, you can take this after that z square calculation, you can take, in both case it will result you that z square will be dominating. If you go for heavy nuclei, z value will be larger, then I can simply write z into z minus 1 as z square. So this term will become just z square. Okay, so AC times z square will come, z square I will take, z square, and this is divided by a raised to 1 by 3. So these are the terms for, this is for that parent nuclei. Okay, and for daughter nuclei, I will just take, let's take, this is for parent nuclei MT, and I will take for daughter nuclei MD. So MD C square will be nothing but these terms remain same, that MT C square, all those things, and C also same, because there is no change in that volume energy term and surface energy term, that is inside this C, constant C. Then we have again that what is this? Is surface energy term. So this is that asymmetric term plus volume term, and that will be S times. Now your A raised to 2 by 3 will become A by 2, because your mass number is now A by 2 for daughter nuclei. So this is A by 2 to the power 2 by 3 minus AC times. So Z will become Z by 2, Z by 2 square divided by A will become A by 2. So A by 2 to the power 1 by 3. So this is the total of that daughter nuclei. So this is for one daughter nuclei. Okay. For two daughter nuclei, if we consider this, these portions remain same. So I have 2 times of this. These portions will be different for 2 times. Okay. So for 2 daughter nuclei as daughter nuclei, if you consider, then only this part will be equal to this part, because at C, volume energy of first nuclei plus volume energy of the second nuclei, second daughter nuclei. Okay, so first daughter nuclei plus second daughter nuclei, that will give you that volume energy of that parent nuclei. Okay, so 2 such kind of things, such daughter nuclei. So 2 times mdc square, and this m0 c square plus c, this will be from both those daughter nuclei. If you add those 2, then you will get that of same as parent nuclei. And then we have this symmetric, surface term and Coulombic term, that is for both those nuclei, that is 2 times of that. That will be different from that of parent, so that's why we are taking it separately. Okay, and now if you want to calculate what is that Q value will be nothing but parent energy square minus that of daughter nuclei energy square. Okay, that will be that Q value, that energy which is released whatever energy which is for parent minus whatever energy of that daughter nuclei, that will be that remaining energy that is used for that kinetic energy of nucleus. So this will give you, if you take the difference, so these two terms will cancel out, okay? And this is the same expression, so we have some a by 2 here, z by 2 and a by 2 here, so only take care of those things. Then you can see when you take that these two difference, that is this two equation you have to subtract, then you will get as times, that is for first for us that surface term, it will come as a raised to 2 by 3 minus a by 2 to the power 2 by 3. Okay, so when you take that minus terms, so this will come, so okay, so there is 1 2 here like this. So when you take that minus, these two minuses are there. Okay, so mc square minus 2, this is 2 mpc square minus 2 mp. So okay, so this is daughter nucleus. This is mdc square. So the term will come like this: as raised to 2 by 3 minus 2 times this. This is for that surface term. Then you have that plus this minus, and the first minus is also there. So this will come as plus. What will be that Coulomb term? So that is AC times Z. So here we have Z square by A raised 1 by 3. So Z square by A raised 1 by 3. And after that we have Z by 2 square to A by 2 raised 1 by 3. Okay. And here also we have that 2. So 2 times of this. I will just write that much more clear. Here we have that 2 multiplication. So coming, so for better clarity, plus minus 2 times, what is that value? A by 2 raised to, so this will come a by 2 raised to 2 by 3, right? And here also we have that minus 2 times z by 2 square divided by a by 2 to the power 1 by 3. So you need this value. This is your Q value. So for energetically feasible reactions, or energetically possible reactions, we can say. So for that, we need this Q value will be positive. This Q value should have to be positive. So that means for energetically feasible fission process, this Q value has to be positive. So then only that energetically it is possible, which means that this should be greater than 0. This value should be greater than 0. Then only that reaction will happen spontaneously, naturally. That is energetically feasible or energetically possible reactions. So this value should be greater than 0. Then only it will happen spontaneously. Otherwise, we have to provide some energy to that reaction, that parent nuclei, by bombarding some high energy neutron or any other particles, okay, then that fission process can happen if it is not, that q value is not greater than 0. So if it is greater than 0, then it will happen spontaneously. Now if you have any reaction, you substitute those a values of parent nuclei and daughter nuclei. Okay, so in this particular case we do not need that daughter nuclei, all those things, because we have taken that as a symmetrical reaction. So we just need that parent nuclei. If you consider, substitute that a values here, here, and consider that z values here, and then substitute all those values and check that whether that q value is coming positive or negative. Okay, once you know that the q value, whether it is coming as positive or negative, then you can say that this particular nuclear fission process is energetically, whether it is energetically feasible or not. Okay. That calculation you can do. You already know that what is the as and ac value that we have already discussed during that liquid drop model. So this as here is nothing but this we already discussed anyway. So this is nothing but will come around 16.4 mega electron volt, and that AC is nothing but 0.72 mega electron volt. This we already discussed that liquid drop model. So this value you have to substitute for this AS and AC, and substitute those A and Z values for any nuclei, heavy nuclei, and then you find out what is that Q value will come, and you can say that that particular nuclei can undergo this nuclear fission process spontaneously. If it is less than 0, such nuclei, then we have to give some energy in order to have that nuclear fission process. Okay, these are the understanding or the conclusion that we have to get from this particular calculations. Okay, so under this condition, if you provide your A value for let's say for nucleus which is having A value, so under this condition, nuclei with A value which is greater than 100 will provide Q which is positive. Okay, if you substitute that A equal to 100, those nuclei with the atomic numbers, then you get a Q value which is positive, which means that any nuclei which are having mass number which is larger than A, which is equal to 100, which is larger than 100 mass number, all those nuclei undergo spontaneous nuclear fission by this calculation. Okay, so from this calculation, if you put A value which is more than 100, then you will get Q value as positive, which means that any nuclei which are having mass number larger than 100 undergoes spontaneous nuclear fission, okay, because their Q value is greater than 0. But in reality, there are many nucleus, there are many nuclei, which are not let's say not undergoing spontaneous nuclear fission. I should say there are many nuclei with mass number A greater than 100 which are not undergoing spontaneous nuclear fission, which means that they are stable. Okay, so there are many nuclei with mass number A which is greater than 100 which are not going spontaneous fission reaction, which are stable in nature with mass number A greater than 100. So there are some some violation to this particular calculation that we did here. So they are not exactly following this particular calculation. So by this theory, this calculation we have, we can get Q value which is positive for all nuclei which are having mass number greater than 100. But in reality, there are nuclei which are having mass number greater than 100 and still stable. They are not unstable. They will not go to those nuclear fission processes, but they are still stable. So we need some other explanation to have a more conclusive more better conclusion for this nuclei which are having more which are more stable with mass number greater than 100. So later on for this explanation, this Bohr and Wheeler come up with some different idea, considering that nuclei is again as a liquid, and they predicted that this nuclei will be undergoing some deformation before nuclear fission. So this nuclei, which will be deforming into some other phase initially, okay, like this. So this is in that initial paranuclei, which is in the spherical form as a sphere, as a liquid drop. Then that will undergo to this shape. Then it will go to some kind of almost like this. Yeah. Try to bigger in size so that that volume will be same. Then it will go to, it will separate into two different. So this is the assumption that is given by Bohr and Wheeler. Okay. So what will happen in this time? Their center, initially it was a sphere. So the center is here. Okay. Then the central position of that is deformed into some different shape. Now the center can be here and here. So they're an average position. Okay, that center that is separated now. So this is that distance of their. Then that is again separated like this. Center of that nucleus. You consider for deformed shape, it will be having two different centers and they are well separated in this stage. And after that, they will separate into two different nuclei. So this is the explanation that that is provided by this Bohr and Wheeler in order to explain why these nuclei with mass number greater than 100 still does not show any fission process and still they are stable. Okay. So we consider this deformation of the nuclei. I should say this is deformation of nuclei. So this deformation before nuclear fission will happen. And when that deformation happens, we have a different parameter which is called as deformation parameter. Deformation parameter. That is nothing but your R that I have given here. This deformation parameter we have to consider. So for spherical structure, this deformation parameter is 0. Okay. And when that spherical structure changed to some other shape, and then after that, that will split into different nuclei. So when this happens, that R will increase, that deformation parameter will increase. Okay. And that we have to plot against that energy of that nucleus. Okay. So let's draw that deformation against that energy. So I will just insert again that axis is line. And two. Okay. Now, if you consider that deformation parameter in that x-axis R, okay, and we have energy in this y-axis, energy of that nucleus. So let's consider this is the energy of the nucleus. So when this deformation happens, okay, initially when it is having that spherical structure, it is having this much of energy. And when that deformation happens, it is energy starts to increase a little bit like this. And then it reaches its maximum and then come back like this. And here it will be something like 1 by r fashion. From here onwards, it will be reducing like 1 by r fashion. Okay. So here those nuclei are well separated. So when you have, okay, this should go like this. When you touch that energy to that zero value, okay, that means that the nuclei are well separated. Those daughter nuclei are well separated now. That this when this touches that that energy, when that energy will become zero, which means that this line touches on that x-axis. At that point, these daughter nuclei are well separated. Okay, so there will be having some Coulombic repulsive force between these two nuclei. So let's say Z1, Z2. If you consider first number of protons in the first daughter nuclei and second daughter nuclei is Z2. Z1 is for first daughter nuclei, number of protons, and number of protons in the second nuclei, which is Z2. Then if you take the Z1, Z2 times E square by 4 pi epsilon 0 R, that is the nuclear, that Coulombic repulsive force that will in between these two nucleus that will happen. And when when they are separated, only this will happen, because when they separate, this Coulombic force will come to picture, and there will be Coulombic repulsive force between these two nuclei now. And Z1, Z2 times C square by 4 pi epsilon 0 R is that potential that will be given. So this energy will be reducing in terms of this 1 by R fashion. Okay. After that splitting. So around here, that is the maximum energy that where you have that maximum energy, you will be having that almost split like structure. So it will be having almost at the end of at the beginning of that separation. Okay, so they'll be having this kind of shape when the nucleus is having that maximum energy, and after that it will get separated and becomes that Coulombic repulsive force comes to picture, and the potential will be varying in form of 1 by R. So energy will be varying from here onwards, it will be varying as 1 by R. So if up to here it is that maximum, then it is going to become 1 by R fashion, decreasing as 1 by R fashion. Okay, so this is the maximum energy when there is no deformation. So this is that without the deformation around this range. Then it starts to that deformation, and we have that maximum energy when it reaches some maximum energy. And if the nucleus goes beyond that level, that the deformation parameter, then again going beyond this value, then the nucleus will separate. Okay, and the difference between these two energy, that is the maximum energy, this maximum energy, and the energy of the nucleus when it is having that spherical symmetry, spherical shape. This difference is called as, these two difference is called as right here, this difference in energy is called as activation energy. activation energy. So this nuclei should have this much of energy, okay, this much of energy for in order to break into two different nuclei, which means that in order to have that nuclear fission, the nucleus with the energy when it is having that spherical symmetry should increase, and it should have energy which is larger than this activation energy. Then only it will be splitted into two different nuclei, and that nuclear fission will happen. So in some nuclei, this energy barrier, we can also call this activation energy as your energy barrier or potential barrier, we can say, that has to be crossed. Okay. So in some, this energy barrier or the activation energy depends on your mass number, that nucleus. Okay. So in some nucleus, this potential barrier, that activation energy will be larger. In some nuclei, it will be smaller. Okay, depending on that nuclear mass and nuclear structure, all those things. So it depends on those nuclear. Mainly, it is a function of mass number. So this energy, activation energy, and this energy versus deformation uh, parameter, that is a function of mass number. Okay, for example, if you consider a value, a equal to some 240, okay, then you need that activation energy will be around activation energy, that will be around some 5.5 to 6.5 mega electron volt. So this nuclei with 240 mass number has to get some 5.5 to 6.5 mega electron volt energy additional. Okay, so initially it is having this much of energy when that spherical symmetry is there. Okay, then if you provide some 5.5 to 6.5 of energy, then that can go to this level, that potential barrier can be crossed and nuclear fission can be possible. Okay, in some nuclei, this potential barrier will be having some smaller size. Some nuclei will be having higher size. In some nuclei with a very large mass number, and there will not be any such kind of barrier or activation energy. So in that nuclei, they will be just going like this. Just they will just going like this. So in those nuclei which are not having this barrier, okay, which are just going like this, okay, so you just confirm this line how it will come. But when there is no barrier, in some nuclei which are having very heavy, very large mass number, very heavy in size, those heavy nuclei will not be having this barrier, energy barrier or the potential barrier. So such nuclei does not need any energy from outside to cross this energy barrier or to have this activation energy. So that is not needed. In such nuclei, the nuclear fission happens spontaneously without any external energy supplied. But in some nuclei, they have this activation, this energy barrier, and we have to provide some energy, then only this nuclear fission will happen. Okay. So now if you consider this nuclear deformation again, you consider this nuclear deformation, then let's consider that first initially that sphere like structure. Okay, this is not that, it is not looking like sphere. I will just do it again. So if you have that sphere like structure initially, let's consider this as sphere, spherical structure. And then there is the radius will be r here. You measure here, it is also r. In all direction it will be r, and you consider that spherical structure, and that is shifted into something else now, like an elliptical shape, ellipsoid. Okay, so then your values will be different. Okay, let's consider this as this. So let's consider this is b, this is b. You just draw it in that way. Okay, so it's just these two should be same, and this is a, so it is having some different shape now. This has changed to this, that deformation I'm saying. Okay, now we have this condition that this volume of the nucleus before deformation and after deformation will be same, that whatever volume of that spherical structure will be the same as whatever the volume of that ellipsoid. So we'll take 4 by 3 pi r cube here, and this will be equal to here 4 by 3 pi, instead of r we have a b square. Okay, so this will be equal because that volume is constant. Since volume is constant, we have to consider this 4 by 3 pi r cube, which will be equal to 4 by 3 pi a b square. Now if you further consider, let's say if we assume that a equal to something like r times 1 plus epsilon, some constant epsilon. Okay, then we can say we substitute this back, let's say 1, this is 2, so 2 in 1, which implies I'm just considering a equal to some r, that is r is the initial spherical nuclear radius. Okay, so that is there. So if you multiply that with some 1 plus epsilon, some constant, then you'll get a, let's assume like that. Then you take this value 2, that is substitute in 1, then you will get what is b, corresponding b. So that will give me b square equal to, substitute here what is a, then that will give me b square equal to r square divided by 1 plus epsilon. Yes, just substitute here, which is r into 1 plus epsilon, and equate these two equations. Then we'll get that r square by 1 by epsilon, r square by 1 by plus, sorry, r square by 1 plus epsilon will come as your p square. Just you can easily do that. It's not a big deal. Just cancel these two 4 by 3 here, 4 by 3, and pi also you can get cancelled, they are constant. So r cube only will come here. 1 r will be cancelled from here. Then it becomes r square by 1 plus epsilon for b square. And from here also you can get b equal to r divided by put 1 plus epsilon. Okay. Now if you consider the surface area, what will happen to that surface area? Surface area will be increased because the spherical structure now deformed into some ellipsoid structure. Then again it will again increase when it splits into two different nuclei. So surface area will increase when that deformation happens. So that surface area will become s times what was that value, 1 plus epsilon. Okay, so it will become 1 plus 2 by 5 epsilon, 2 by 5 times epsilon square plus etc. Higher order terms also will come. Okay, so initially your surface term was a0 a to the power 2 by 3. That will become this was when it was having that spherical structure. Now that is then again deformed. After deformation, that will become the same, a0 times a raised to 2 by 3, but you have this additional term 1 plus 2 by 5 epsilon square. There are higher order terms that we do not consider now because epsilon we took very small. And then we consider for Coulomb term, okay, your Coulomb term also AC Z square divided by A raised to 1 by 3. That will become in the same action, but in the case of Coulomb interaction, that Coulomb interaction will become will be reduced. Okay, as I said earlier, when the fission happens, when the deformation happens, that shape surface energy will increase. Okay, and that Coulomb interaction reduces. Coulomb interaction decreases. Okay, so that will result AC equal to Z square by A raised to 1 by 3. That term that will change into, okay, this will change into same form it will come. So AC Z square by A raised to 1 by 3. Still it is not splitted, it is not separated. So it is just Z square by A raised to 1 by 3 times. In this time it will be decreased. So 1 minus, so initial value is AC Z square by A raised to 1 by 3. That will come when you take that product with this one. Okay, minus some AC Z square by A raised to 1 by 3 times 1 by 5 epsilon square. And there are higher terms that we will not consider here. So net increase will be nothing but your AS times A raised to 2 by 3, this much times 2 by 5 epsilon square, if you do not consider that higher terms. This minus AC times Z square divided by A raised to 1 by 3. Then remaining will be this term minus 1 by 5 epsilon square. So this is the net difference, net increase that will happen when that deformation comes to picture. Okay, when that spherical geometry turn into that deformed nucleus. So there will be a change in your symmetric energy as well as in the Coulombic energy. And you take this difference, okay, you take this difference, that is that net increase in that energy terms, that Coulombic and surface energy term. So there will be always a competition between the surface energy and Coulombic energy term. And these two terms will give you that positive Q value and negative Q value, these two terms. So it depends on these two, Coulombic interaction as well as the surface energy, Coulombic energy term and surface energy term, that will give you that the value of Q value and all those things. So if this, let's say, if this is less than 0, if this is less than 0, which means that there is no barrier. Which means that there is no barrier. Okay. So what actually this is, this will give you that energy, activation energy, that is the deformation. And you see that from that figure, if you consider that energy versus deformation R, then you have this increase and it is decreasing. So this suppression of energy, so initially it was spherical. So spherical means this portion, this much of energy. So at this time you had that Coulombic term and surface term. Okay, those terms, it is just this AC Z square by raised 1 by 3 times 1 is 1. Okay, similarly for that for surface energy term also, when there is no deformation, then you have only this A0 A raised 2 by 3 times this 1. Okay, that is your surface energy. But when there is deformation, you have additional term 2 by 5 epsilon square that has to be added with your initial value A0 A raised 2 by 3. Similarly for Coulombic term, you have this term AC times Z square A raised to 1 by 3 times 1. as your spherical nucleus for the nucleus for spherical nucleus. But when it deforms, that is subtracted with 1 by 5 epsilon 0 epsilon square times AC z square a raised to 1 by 3. So that is decreased. Coulombic energy term is decreased before because of that deformation. So when that deformation happens, you have excess energy. So that excess energy, net increase in that energy is given by this equation. Okay, from this equation, that is from that surface energy and Coulombic energy difference. Okay, that is coming in this energy. So that activation energy that is coming from here, from this difference. Okay, so if that is zero, so if this term, if this difference is going to become zero, which means that there is no barrier. Okay, so there is no barrier has to be crossed. In such nuclei, the nuclear fission happens spontaneously. Okay. Now, if it is not less than zero, okay, if it is not less than or equal to zero, then in such cases there will be barrier, and you have to provide some energy in order to have this nuclear fission process. Okay? Let's say if there is no barrier which is less than zero, which means that when you equate these coefficients, all those things, and this will implies that z square divided by a, for this condition z square by a should be greater than that 2as divided by is for this when you need that it should be less than 0. Okay, for this condition. Okay, for this condition you substitute the values here. So in order to make this equation, that difference between surface and the Coulombic energy terms after that deformation, that net increase. Okay, so that net increase, from that net increase, if it has to be less than 0, then your condition is that z square by a should be greater than 2as by s. Okay, so this will give z square by a, this term should be greater than, if you take this ratio and multiply with 2, then you will get this is 47. So nuclei with this condition z square by a, which is greater than 47, will undergo spontaneous nuclear fission because there is no barrier. Okay, so theoretically, let's say if your z value equal to some something, so okay, from here we can see z square by a is greater than 47. Okay, so let's say your z value is some 0.4 a. Okay, then z square by a will become z square by a, that will be nothing but 0.4 square by a, this much of a square, right? And if this has to be greater than 47. Okay, then under this condition your a should be almost in this condition it will be greater than, then your a should be greater than 300 in order to get this condition 47. So here one a you can get cancelled, so it will be like a 0.4 square times a, and in order to have that value greater than 47, your a should be at least 300. So it should be more than that. Okay, a greater than 300 should, then only you get this condition, z square by a will become greater than 47. So those nuclei, okay, this is just an assumption. So those nuclei which is having this condition, that z square by a which is greater than 47, that will go to the spontaneous fission reaction. We do not have to supply an energy for that particular nuclei, and they will undergo spontaneous nuclear reaction.